So here we'll try to derive the relationship between the correlation coefficient and the regression coefficient. So let x and y be two random variables. Now the correlation coefficient between x and y is given as R is the covariance between x and y divided by the product of the standard deviations of x values and the standard deviation of y values. Let us call this as equation 1. Now the regression coefficient of y on x is given as the covariance of x and y divided by the variance of x. Let us call this equation 2. So we'll use these two formulas to derive the relationship between the correlation coefficient and the regression coefficient. So from 1, we know that R is equal to the correlation coefficient is equal to the covariance divided by the product of the standard deviation of x and standard deviation of y. Now this can also be rewritten as follows. Okay, because we know that if this is just a slight manipulation, because we know that this side and this side can be cancelled, and we're left with this, which is the same as this value. So it doesn't change much, but this is just a slight manipulation where we are rewriting the correlation coefficient in this form. So what we can do here also is bring the standard deviations together. Bring the standard deviations in the denominator together. Okay, and what we get is covariance xy and what you get is that, and this is nothing but the covariance of x and y divided by the variance of x, and this is the same, which is nothing but the value of the regression coefficient of y on x. So this way we've expressed the correlation coefficient in terms of the regression coefficient. Okay, now we can also represent or express the correlation coefficient or the regression coefficient in terms of the correlation coefficient. So let us use equation 2, where we have the correlation coefficient of y on x as follows. And here also we can rewrite this as this form. Again, it doesn't make any difference, because if we cancel standard deviation y by standard deviation y, we get 1, which is the original formula. So this is just a slight manipulation. So here what we do is we break this square. Let me write this properly. We break this variance, or the square of the standard deviation, into two parts. And what we can also do is bring the standard deviation of y to this side and standard deviation of x to this side. And if you remember, this part is nothing but the correlation coefficient. So this way we have expressed the regression coefficient in terms of the correlation coefficient. Now we can also show that the correlation coefficient is equal to the regression coefficient of x and y times the standard deviation of y by the standard deviation of x. So here it's the same, but just a little the manipulation is different. So you have x, y, standard deviation of x, standard deviation of y. So what you can do is you can manipulate this. Now before we manipulated this by taking standard deviation of x. Now we'll take the standard deviation of y in the numerator and denominator, and what we get is can bring the y values together to this side. Standard deviation of x over here, then standard deviation of y, and what we get is covariance xy. So standard deviation y, standard deviation y, this is nothing but the variance of y. So this is the regression coefficient of x on y. So that is the relationship between the the correlation coefficient and the regression coefficient of x on y. So similarly, we can show the relationship between the regression coefficient of x on y with the correlation coefficient. The same way as before, but the manipulation is a bit different. We just exchange the way, because in the previous case we've made use of the standard deviation of x, so here we'll make use of the standard deviation of y. And over here it's almost the same, just the way we are manipulating the formula is a bit different. So in the previous case we used standard deviation of y, standard deviation of y. Here we'll use standard deviation of x, standard deviation of x. So what you can do is you can split this into two parts, and now you can bring standard deviation x, standard deviation of y together. This will go here, and that is how you establish the relationship between the regression coefficient of x on y with the correlation coefficient. So now we have shown that regression coefficient of x on y is equal to the correlation coefficient times standard deviation of y by standard deviation of x, and the regression coefficient of x on y is the correlation coefficient times the standard deviation of x by the standard deviation of y. We get the product equal to r square. Now this r square, now remember, if you want to remove the square, let's say if you want to move the square from r, which is on the right side, we have to we can remove this square, we can remove this square only if we take the square root, because if you remember, the value of the square root is half. So which means what we're doing is writing it in this form. So we cancel this 2 and 2, we get the value r, and to do that we have to square root both sides. Of r square. So therefore r, we've expressed r as the square root, as the geometric mean of two regression equations. Okay, so this This relationship is important, especially if we are if we know the regression coefficients, okay, and we are asked to find the correlation coefficient. So let's take an example. Now suppose we have this sum. We have this sum where we are given the regression coefficients of x on y and y on x, and we have to find the correlation coefficient. So we have to find r, and what we have is our regression coefficient of x on y is 0.904. So bxy is equal to 0.904, and the regression coefficient of y on x is 0.697. So your byx is equal to 0.697. So we already have established the relationship that the correlation coefficient is nothing but the geometric mean of two regression coefficients, which is bxy multiply byx. We just substitute the values. We already know what is regression coefficient of x on y, regression coefficient of y on x. So this gives us the square root of approximately 0.630088. So therefore your r value, or your correlation coefficient, is equal to 0.79. So that relationship is important. So let us take an example where we have regression equations instead of regression coefficients, and we have to find the correlation coefficient. We've already established that the correlation coefficient is the geometric mean of two regression coefficients. So here we are given two regression equations. So let us solve this. So what is given is the regression equation of y on x, and we have the regression coefficient of x on y. Okay, so from this equation, x equal to 1.2y plus 86.5, this part here is nothing but the regression coefficient of x on y. So here your regression coefficient is equal to 1.2. Now the other equation is given as follows. Now to determine the regression coefficient of y on x, it is important that the coefficient of y is equal to 1. It is, again, let me repeat that, the coefficient on the left hand side, which is the coefficient of the dependent variable, should be 1. So what we do is we divide both sides by 10, so that the coefficient of y becomes 1, because we already have 10. So what will make this 10 equal to 1 if we divide it by 10? So remember, but we have to divide both sides by 10, and what we get is y is equal to 0.5x. This is too early, should have been here, plus 36.7. So now this 0.5 is your regression coefficient of y on x. So therefore byx is equal to 0.5. So now simply we can use the relationship between the correlation coefficient and the regression coefficient, where r is the arithmetic mean of two regression coefficients. So this is equal to 0. So first write the x values. bxy is equal to 1.2, byx is 0.5, which is equal to square root of 0.6. So therefore your correlation coefficient is equal to 0.77. So that is how you find out the correlation coefficient when you know when you either know regression equations or when you know the regression coefficients.